Okay. All right. Let's talk a little bit about numerical methods for dynamics. The idea is that we are going to see from essentially how to get to the finite element equations. Farbod already said my specialty is actually finite element methods. That's where my main area of research lies as well. And so we are developing new formulations, and we're of course applying these formulations to all sorts of different problems. And what I want to show you today is how do you actually solve dynamical systems when you discretize a problem with finite elements. So of course there is a lot of theory, right? As I mentioned, we're going to record the session so that if anything, you can always go back to the recording and then see what we discussed. But from the let's say the strong form of the problem, we're going to discretize the problem using finite element spaces, and then once we have the discretized system, the idea is that we are going to be able to solve them using time integration. So that is the whole idea. Okay, so let's get started. This is an overview of what we're going to do with the theory. We're going to do elastodynamics in 1D. And again, we're going to show the process, how you start from the actual equation of motion, the dynamic equilibrium equation. And then we say, well, maybe this equation is very hard to solve, or maybe it is very, very hard to obtain the exact solution to the problem. And so normally what we do, we try to cast the problem in a different form. That is a so-called variation or weak formulation. So we're gonna go into that as well. And then that equation cannot be solved yet because we don't have infinite resources, right? So we need to discretize the equation to be able to do some number crunching in a computer. And so this is where we apply the so-called Galerkin projection to lead finally to the finite element discrete equations. And once we have them, we can finally get to solve them. Not really, because we need to, so if you think about the dynamic equilibrium equation, you have essentially the displacement, velocity, and acceleration. So you have one equation and three unknowns, right? So you want to combine this dynamic equation with something else. And so we're going to discuss Newmark's family of methods, which is one way of solving the dynamical systems. But in the beginning, we start with elastodynamics in 1D so that you know exactly where everything starts. From the very beginning, we're going to start with a bar in 1D, which is the simplest case in mechanics. Then we're going to extend that to 3D, and you will see that many of the things that we do in 1D translate very nicely to 3 dimensions. So with a couple of subtleties here and there, pretty much everything remains the same. And once we have that, we're going to delve into time integration, and in particular to the Newmark's family of methods. And we're going to discuss their different properties. There are many different methods in this family, and so we are going to discuss which one performs more or less okay, which ones are stable, which ones are unconditionally stable, and so on. Okay. Of course, you are free to interrupt me at any point, right? If you don't understand something. The idea is that since we have 3 parts, we're going to go through the first part. We're going to have a little break, and then 5-10 minutes later, we're going to continue to the second part and so on. But feel free to interrupt if you have any questions, or if you think that I am going maybe a bit too fast, just stop me. That's sometimes I tend to go fast because I assume that you guys know about finite elements. So who knows about finite elements here? Yeah, okay, so you know about finite elements. So maybe that is great. That allows me to speed up a bit sometimes. Okay. All right, let's start with from the very beginning. As I said, let me see. I'm gonna go out of the internet so no one bothers. So in the very beginning, I said we're gonna start with a bar. It's basically the simplest mechanical element that you can think of, right? It's a structural element, can sustain only an axial force, so you can take and have the bar in tension or compression, so it cannot get simpler than this, okay? But we start from here because everything that we do in higher dimensions is really analogous to what we're going to do in 1D. Okay, so imagine you have the bar. So this is your bar. We're going to clamp it to the left. So this is basically saying this is a fixed prescribed displacement. Here I am applying an axial force, right? So the bar is in tension, as you can see. I'm going to have some mass or let's say force per unit length that you see here with the symbol B. And I'm going to denote my bar with omega. So that is basically the domain of interest. So I say, well, consider a bar omega. It is basically a subset of the reals, so starts from 0 and L. And this is normally, you're going to find that many times when you read books or papers on finite elements, you have the domain like this, but then you have the closure of the domain. And this is basically a bar on top of the domain, and that is essentially saying, well, I'm going to consider the open set plus the endpoints. So this guy here does not consider the ends of the bar, while this one does, right? So I'm considering the endpoints 0 and L, okay? That's all it means. And so normally people like to define the boundary this way, because if I take this set and I subtract that set, all I'm left with is the endpoints, right? And that is what you see here with your gamma. Gamma is basically the boundary, so it's only comprised of the end nodes of the bar. So the bar has mass per unit length m, cross-sectional area A, and elastic modulus E. And so of course, everything can be a function of position, so it doesn't necessarily have to be constant. But we're going to clamp on the left, and then we apply an actual force at the right end. We will see what these are. These are our boundary conditions. And that's it. Well, let's see how we can derive the equation of motion for this very simple element. Okay? Of course, in the end, what we want to do is to find the displacement as a function of position and as a function of time, right? So we have, in essence, not a boundary value problem, but an initial value problem. And so we start by looking at how to obtain the dynamic equilibrium equation. So, well, we isolate a very small piece of the element of the bar, and then this is this schematic here on top is showing the forces. Of course, we apply Newton's second law, and then what we find is that n of x plus delta x, which is the force at this location, minus n at x plus bx dx is equal to what would be the mass per unit length. If I multiply that by the length, then I get the total mass times the acceleration of the bar. Very, very straightforward, just second Newton's law. And of course, a double dot here denotes the acceleration. So if I divide everything by dx and I take the limit, well, what you see in this term is essentially the definition of the derivative, so the variation of the axial force with respect to x plus bx is equal to m times u double dot, and this is the dynamic equilibrium equation, right? So at every point along this bar, ideally, we want to obtain a solution that satisfies this equation. So when I obtain the equation u of xt, if I plug it in, it should satisfy that equation. So that is the objective, let's say, to solve the problem in what we call a strong form, okay? So this is the dynamic equilibrium equation, and of course, we can work a little bit on that equation because we were expressing everything in terms of axial forces. But if now we assume that we have linear relationships between stresses and strains, right, through Hooke's law. So this is, I'm going fast because this should be very known to all of you. Everybody with me on this? Yeah? Okay. If you don't know this, just let me know. This should be a recap of something you have seen in your studies so far, okay? So E is Young's modulus, and so epsilon, which is a strain, is du dx. Then the force is just simply sigma multiplied by A, so stress multiplied by the air, that gives you the force. And then if I take Hooke's law in, then the actual force is Ea du dx. So when I plug that back into the equation, then I get my final equilibrium equation in terms of the displacement field. Notice that there is a second order derivative on u. And this is important because normally when we are dealing with finite elements, we don't want that. And I'll explain in a few minutes why. But again, the idea is that we need to solve for the displacement u such that this equation holds for every xt in omega cross 0t. T is basically the maximum time that I want in my time interval. So that would be solving the exact problem, right, in strong form. But still, we don't have the strong form. The strong form of the let's say, initial value problem is not only comprised of the differential equation. We need all the things. What else do we need? Boundary conditions and initial conditions, right? So, if we state the strong form, we need the equilibrium equation, and then we supplement that by initial conditions. So we have to state that the displacement and the velocity are some known value at 0 normally. And then the boundary conditions, what you see, the first one is we're prescribing the displacement. Gamma D here is going to be the portion of the boundary with Dirichlet boundary conditions, or essential boundary conditions, or displacement boundary conditions. So in this case, I'm prescribing the left of the bar to have 0 displacement. So that is a strict constraint on the bar. The bar cannot move anywhere at that point, right? So this is our essential boundary condition. And then the second boundary condition here is I'm prescribing the axial force. In the example that we have, we are prescribing that at the right end. And so this is so-called Newman boundary condition, right? It's a boundary condition on the dual variable, the displacement being the primal variable, the force is then the dual variable. And so gamma n here denotes the Newman part of the boundary condition. In our case, again, is the right end of the node. Now, this is really stating everything, right? Everything that we can have to solve a problem in strong form. But as I said, it is often really hard to get the exact solution, right? So we don't like to work with a strong form. So in 1D, it may be very easy. Let's say in statics, it's trivial to get the strong form solution, right? If you go to dynamics, things get complicated. But when you move to higher dimensions, it is nearly impossible to obtain the exact solution, right? And so perhaps one of the great inventions of mechanics was the Galerkin projection, right? And I say that, in fact, there are multiple methods that are related in a way, but the Galerkin projection is what allowed us to get the modeling capabilities we have today, right? So to cast this problem in a different form so that we can actually solve it is one of the greatest inventions in mechanics, okay? So let's talk about that. So we said, well, I write here, because it is often not possible to solve the strong form, we pose an alternative form of dynamic equilibrium. In fact, it says the strong form requires higher regularity, smoothness, and is not directly suitable for standard Z0 finite elements. Well, if you think about in finite element analysis, we are normally using linear or at best quadratic finite elements, right? Also, say we take linear elements. We saw that we have a requirement on a second derivative of the field, right, in our differential equation. So we can no longer use a linear shape functions in our elements. And so by casting the strong form in a different way, right, as we will go in a minute through this is a variational form, we are able to lower the differentiability requirement on what we are going to be calling the trial solution, right? So when we discretize our systems, we're going to understand that there may be an error associated with our trial solution, right? And is that good or bad? Well, it depends, right? If you can actually understand the error and know how to reduce the error, it's actually great. If you have zero control over the error, then you don't understand what you're looking at. You don't know whether your solution makes sense at all, right? And so the Galerkin projection allows us to reduce the differentiability requirement on our trial solution. This allows us to use linear finite elements to obtain the solution. And then, well, the basis of the finite element method is you would expect that as you reduce the sizes of the elements, what's going to happen with the error? It gets smaller, right? That would be what you would expect. And indeed, that is the case. That is the basis of the H version of the finite element method. There are other flavors of finite element methods out there, but we're going to discuss in this lecture only the H version. All right, so how do we get to the variational form? Well, very straightforward. We use something called the method of weighted residuals, right? The idea is that we take our differential equation as we obtained it, we multiply this by a weight function. That's why it's called the method of weighted residuals. This is also called a test function, right? We integrate over the domain, and we set that product equal to 0 for all weight functions in some space of functions. And we're going to talk a little bit about spaces, because it's important to understand what is the class of functions that we're going to be using for these problems, right? We cannot just simply use any function. There are specific functions that we have to use. And so that is the basic idea. So in essence, this, what you see here, is an orthogonality condition, right? So I'm essentially saying that this function W and this differential equation, right, the dot product evaluated in the domain of interest, has to be equal to 0. That is an orthogonality condition. It's like, imagine in Euclidean spaces you have two vectors, right? If the dot product of those two vectors is equal to 0, that means that they are perpendicular to each other. So in essence, if we translate that, it's a bit difficult to imagine this, right? Because now we're dealing with functional spaces. These are not Euclidean spaces anymore. But if we imagine what we just discussed, this orthogonality condition says that somehow this function W has to be orthogonal to this residual. I call it residual, and people call it residual because when we plug in something that is going to be a trial solution, that thing is not going to be satisfied exactly. It's not going to be equal to 0. So it's going to be some sort of residual, right? So what we're saying here is that my weight function, in a way, has to be orthogonal to my differential equation. Orthogonal. And actually, it's not a weight function. It's an entire group of functions, because basically I'm using this statement at the end. It says for every W in some conveniently chosen space. Essentially what I'm saying is this has to be orthogonal to a space. And this orthogonality condition, what it does in the end, and there are theorems that prove this, is going to end up picking the best function U to make this happen. And this is incredible. It's really the cornerstone of modeling today. This is what leads to everything that you do in modeling, right? The fact that this equation here, this orthogonality condition, is going to end up giving me the best possible solution U, again, in some conveniently chosen space, means many things. It means that you take the solution to your problem is going to minimize the error with respect to the exact solution. So from infinite number of possibilities, it's going to pick the one that is going to minimize the error with respect to the exact solution. And this is crazy. Crazy. Okay? Well, how big is the error again? Doesn't really matter, right? As long as you can evaluate the error and you can control the error, you can see, well, maybe here I have to do something else to reduce the error, then you have full control over the modeling, all right? So far, so good? Yeah? So let's talk a little bit about these U and V spaces, right? Because it says here, conveniently chosen, kinematically admissible, smooth. There are many, many requirements for these functions, right? Function spaces. Yeah?
Can you explain what you mean by a function space?
Yeah, we will talk about function spaces. So the question is, what do you mean by a function space? We will definitely talk a little bit about function spaces. We are not going to go very deep into the mathematics of this, but I will share with you the basics of what we mean by all of these requirements on functions. Obviously, you have to choose functions that satisfy your boundary conditions. Otherwise, you are solving a different problem. Obvious, right? That's why it means kinematically admissible. Obviously, the functions have to be smooth. Why do they have to be smooth? Well, you don't want to work with functions that blow up in your domain, right? That go to infinity, for instance. Or, if it is hard to differentiate, if the derivatives are not defined at some point, you're going to have to do something special about that, right? And it can be done, but you have to be a little bit careful with this thing. So better if the functions that you're using are smooth, right? All right, so let's work a little bit on this expression. Why do I want to work a little bit on that expression? Well, if you notice, we have a second differentiability requirement on our function U, right? Whereas the function the weight function, it doesn't have any differentiability requirement. So we're going to do integration by parts. This is the result of integration by parts already. And you see that when I apply integration by parts only to this term, right, because this is the one that has the second differentiability requirement, what you have is, in essence, is that we are able to balance the derivative. So now I have a single derivative on u, I have another single derivative on w, right? So I'm balancing the derivatives. This is actually great for many reasons that I will share in a minute. But another important thing that happens when we apply the integration by parts is that we have this term popping up, right? And if you recall, EA du dx is actually the force, right? And of course, the force has to be evaluated at the extremes of the bar. So what we have here is essentially that just simply by doing integration by parts, what pops up in the formulation? The boundary condition, the Newman boundary condition pops up. Well, and someone may ask, well, why not the Dirichlet boundary condition? Well, it's also the Dirichlet boundary condition, because what is the force at a point where you're prescribing the displacement? How do you call that? The reaction, right? So you have the reaction popping up. So in essence, just simply by applying integration by parts, you get this term, right? Where when you replace by what it is, because it's the actual force at L, in our case, remember that we're calling that N bar, right? It's the value that we're prescribing of the force. And then on the left, we have the reaction. But as a bonus, we have this term, and you can see that it has balanced the derivatives. We always want to do that. Now, because now we have a single differentiability requirement on u and on w, we can choose what to solve the problem? Linear functions, right? So suddenly, for the first time, we can use linear finite elements. We can express our interpolants as linear fields inside the elements. Because, well, if I have the derivative, well, it's going to be constant in the integrand, but I can still get something useful out of it. And for the most part, we end up using linear functions in finite elements. That is normally what we end up doing, unless, of course, you are doing research and you can do all sorts of crazy things that I'm not going to get into, but it is possible to choose anything, any function, as long as it doesn't blow up, as I discussed, okay? All right, so now that we have this term, we plug it back into the equation, and let's talk a little bit about function spaces. So what are the requirements that we need for these functions? Well, in finite element modeling, we use something called Sobolev spaces. And, you know, of course, I'm going into the field of mathematics. If you're coming from the field of mechanics, you normally hear that you have, for instance, D'Alenbert's principle or the dynamic principle of virtual work, right? And people say, well, you have to choose functions that are sufficiently smooth and kinematically admissible. This is what people normally say. But formally, like if you really want to look at how mathematicians look at these problems, they use Sobolev spaces. So what is a Sobolev space? Well, the Sobolev space is defined as, so if I say, for instance, H1, this is the first order Sobolev space, is comprised of functions that are square integrable, and square integrable just basically means that if I take the function, I square it, and I integrate it over the domain, the result of that integral is just going to be finite, right? I'm going to get a value. So the Sobolev space is comprised of functions that are square integrable, and also the derivative of that is going to be square integrable. That's all it means. So when you ever see in a paper or in a book Sobolev spaces, wow, it's crazy, it's very hard. No, it's not. It's just simply that if you take the function, right, and that function you're saying, well, this function is in H1, well, if I take the function and I square it and I integrate it, the outcome is just finite. It's not going to blow up to infinity, the integral, right? And similarly, if I take the derivative, because again, it's in H1, that integral is going to be finite. The result of that integral is going to be finite. Now, if I say, how about H2? I have to have the function being square integral, the derivative being square integral, and the second derivative of the function being square integrable. That's all it is. So these are the functions. So when we say sufficiently smooth, we already assume that there is going to be some regularity in the solution, some smoothness in the functions that we use, right? That you can actually obtain a finite value. So let's say if I go back, for instance, to this term, well, if you notice, I'm going to be integrating the derivative. So obviously, I want that integral to be finite, right? In essence, this term here is the internal energy of my body. And it makes sense that my internal energy remains finite, right? What happens if I have infinite energy? Can I have infinite energy? No. What happens to the bar if I continue increasing the stress or the strain? Huh? Well, it's going to break. There is nothing that can sustain infinite energy. So a priori, doesn't even make sense to choose functions that are going to blow up, right? From the mechanics point of view. And so we stick to functions that are square integrable. So that is basically the quick note on spaces. And well, we are going to define now the final function spaces that we're going to use. So we define this space V0. V0 is essentially a function space that says I'm going to pick functions that are in H1. Again, functions have to be square integrable. The derivatives of those functions have to be square integrable. That's all it means to be in H1 of omega. But I'm going to add another requirement. I'm going to say that the function has to be equal to 0 in the Dirichlet part of the boundary. I make specific requirement that the function is going to be equal to 0. And why do I do that? Well, because if I do this, if you look at the previous equation, if I make this function, remember this was a reaction force, right? But if I make this function equal to 0, what happens to the reaction term? It drops. I don't need to deal with the reaction anymore in the formulation. So this is a simplification that we normally do in finite element analysis. Otherwise, you have to add another equation to be able to deal with the fact that you have the reaction in the formulation, and we don't want to do that. So finally, my weak or variational form of dynamic equilibrium, right? Remember that when we set up the weighted residual, we are weighting W with the differential equation, right? And we're integrating over the domain of interest, and we're setting that equal to 0 for all these functions. And essentially, we are going to obtain the dynamic equilibrium on average. So that is the whole objective. We are no longer requiring that the function that we obtain is going to satisfy our dynamic equilibrium equation point-wise along the bar, but now we're going to be happy if it does so on average. That is the whole idea. Now, there is a little subtlety there because you can actually prove that the strong form and the weak form are equivalent statements of dynamic equilibrium, equivalent in the sense that you can go back and forth between the two, right? Because the variational form, we're still living in an infinite dimensional space. So this is very abstract. I'm getting a little bit crazy here, right? We are living in infinite dimensional space. That means that even with this formulation, you are still able to pick the exact solution of the problem. So that is why there is an equivalence between these two problems. But in reality, when we want to really solve the problem, we have to lower the dimensionality of our problem, and then we choose finite dimensional spaces, and now we have an error, okay? You're all with me on that? Yeah? So far, variational form, strong form are, in a way, equivalent statements. You can go back and forth between the two, and there are theorems that prove that in books. But the moment we lower the dimensionality, and then we can crunch numbers in a computer, then that is no longer possible, okay? And most likely, you don't get the exact solution. You get a solution. This is good. We don't know. We can control the error. We refine. Does it improve? Yeah, more or less. So we refine again. We have criteria to do convergence, right? We can have these a posteriori error estimates in our finite element mesh and then say, well, maybe if I refine on this area, it's going to improve. Yes, it does. So we can control the error. All right? Okay. So basically now our final version of the weak or variational form is stated here. You notice that on the left, we have two terms, right? The first term is essentially going to be our, let's say, potential energy. This is the strain energy of the deformation is going to, is basically that term. Then we have a second term here, which is the inertial term, right? So essentially, you can already see that this equation is going to lead to certain structures, right? So here, this term is going to lead to my so-called, no one? Stiffness matrix. This term here is going to have the mass matrix multiplied by the acceleration. And then we have on the right-hand side, we have some loading, and that is going to be my
Right-hand side.
right-hand side is called the, who said that? Force vector. Thank you so much. Yeah, so this is going to lead to a structure already. Again, we are not there yet, because in order to get that algebraic equation, we have to do what? We have to go from infinite dimensions to finite dimensions. And that is the Galerkin projection, right? Okay, so boundary conditions, as we said already, arise naturally after performing integration by parts. We already discussed this. And now we have to discretize it. Now we really get into picking the right finite dimensional spaces, right? As we said already before, these Sobolev spaces, the requirement was that they had to be square integrable. But there are so many functions that you can pick, right? That are square integrable, that are in H1. So many different functions. So, okay, now we make a concrete choice of the functions that we want to use, right? So now, everywhere where you see a superscript H, that means that we are using a finite dimensional form of that, right? So for instance, my UH here is going to be my finite dimensional space. In fact, it's going to be my finite element dimensional space, right? Finite element, finite dimensional space, right? So the same as VH. That's why I'm writing here. This is actually, this UH and VH are actually subsets, because it's a small portion of the actual Sobolev spaces that you are required to use to solve this problem, right? So now, again, H means discrete, and we choose H as the symbol because H denotes what in finite element analysis? The mesh size, right? Normally, that is the symbol that we use to denote the mesh size. All right? Now we're going to be calling this a trial solution, right? It's not anymore the exact solution. The moment we go down in dimensions, again, we cannot call it the exact solution unless you are very lucky and the problem is so simple that you can still obtain the exact solution. But from now on, when we are in a discrete dimensional space, we're going to call this the trial solution, right? Trial solution, well, because you can try this one or you can try that one, and yeah, you're going to get something better. So that is our trial solution. And as we discussed already, the fact that we were able to lower the differentiability requirement, that enables us to use linear shake functions for finite elements. And so that's what we're doing, right? So we take the bar, we discretize it in a few elements. You see here 4 elements, so we have 5 nodes. And you see that I wrote here the functions that are associated with each one of those nodes. These are the so-called hat functions. Some call them roof functions. Some call them, bilinear functions. There are many names, but they are the simplest functions that you can pick, right? They have really nice properties. They are very simple. They're very straightforward to work with. Derivatives are constant, so cannot get simpler than this. So it's very nice to, you can even do handwriting closed form solutions using these functions. So they are great to do like little tests. And so now my trial solution, I'm going to write it basically as the sum of shake functions multiplied by coefficients. So those are scalars. These WIs here, these are scalars, or let's say coefficients that are multiplying my so-called shake functions. I do the same with the trial solution, right? So it's basically the sum of phi ui. Ui, again, are here my coefficients. Those are sometimes called degrees of freedom, right? In particular, for this type of choice of shake functions, those are also going to be called the what? The displacements. And it's only here, and for this particular choice. And the reason is, well, if you look at the properties of these functions, right? These functions have a really nice property. It's called the Kronecker delta property. right? And the Kronecker delta property is basically the function phi I evaluated at nodes xj is equal to the Kronecker delta. That's why it's called the Kronecker delta property. That basically means that if I take function phi 3, the function is going to be equal to 1 there, and it's going to be equal to 0 at every other node. So when I want to find out what is basically the displacement at this point, and I replace in this expression here, I replace, right? All the functions are going to be equal to 0 at that location, except for one that is going to be equal to 1, and therefore that degree of freedom that is associated to that function physically represent the displacement of the field at that location. That is why in this context, and in this context only, we can talk about degrees of freedom being displacements. Normally, when we go to more advanced formulations, that is no longer the case, right? That doesn't happen. Many things break down. Degrees of freedom no longer have the physical interpretation that you normally give, right? And yeah.
But I thought it's like the Kronecker delta function is a requirement for a shape function.
No. No. The question is whether the Kronecker delta property is a requirement for shape functions. For Lagrangian elements, normally this is what happens, but finite elements, it's a huge field. You can actually use anything. You can lose the Kronecker delta property. You can have many functions that lose the so-called partition of unity property, which is also a nice property of this function. So what is a partition of unity? If you pick any point along the bar, the sum of functions add up to 1. Any point, right? Like if you look at the center, well, here phi 1 is equal to 0.5 and phi 2 is equal to 0.5. But the addition adds up to 1. That is a so-called partition of unity property. Yeah, you can choose functions like these ones that have the Kronecker delta property and the partition of unity property, but in general, there are many other types of formulations for which that doesn't hold. And if you want to find what is the displacement here, right, you're going to have to evaluate the entire expression. Okay? All right. So far, so good. We have discretized our bar. We have 4 elements. We have 5 nodes. That basically means that we're going to have what type of dimensionality in our final problem. So I should be able to get to an algebraic system of equations of size.
4 by 4 or by 4.
Why 4 by 4?
Because you have one constraint.
Well, that's a good answer. Yeah, it's actually in the end ends up being 4 by 4. But it's a 5 by 5 system. We have 5 degrees of freedom. It's just that it happens that we know the value of one of them. So indeed, eventually, it's a 4 by 4 system that we have to solve, right? In fact, computationally, normally we don't do it like that, right? We do something to the matrices so that you're still solving a 5 by 5 system. It's more efficient. Instead of separating the matrices in parts that you know and you don't know, normally we modify the original system and we end up solving the original size. But Alejandro, that is very inefficient. No, not really. The boundary conditions are always applied to a lower dimensional manifold, which ends up being a very, very small subset of degrees of freedom. Yeah? Okay. So how do we do the number crunching? Well, now that we decided I'm going to express my trial solution this way and my test function that way, right? Well, it's simply a matter of doing some number crunching. So we use matrices and vectors to put all of these together in a nice way. So I'm going to represent the shape function vector this way, like a row vector, and my degree of freedom vector or my displacement vector in this context only as a column vector. And so the product of these two, I can write it like this. Right? And so I can do the same for the test function, right? Phi times W. Again, W is just a vector of coefficients. U is a vector of coefficients, in my case, the displacement that I'm interested in. And so, of course, if I can transpose of this, it's a scalar, so I can use a transpose of that, and then I get the same result, right? And so, again, U, as we discussed, is a degree of freedom vector. Phi is my shape function vector. And this approach is actually called the Bouvinov-Galerkin approach, and I'm not going to discuss too much about this, but the fact that I'm able to write both the trial solution and the test function in the same way, I'm choosing both functions to be from the same space of functions, that is called Bouvinov-Galerkin. Again, finite element is a wild field. You can do all sorts of crazy things. So you can pick, for instance, trial solutions from one space, and you can pick the test functions from a different space. That is something completely different. It's not called Bouvinov-Galerkin. If someone knows, it's called Petrov-Galerkin. Thank you so much. And if, for instance, Petrov-Galerkin was the solution to using finite elements for computational fluid dynamics. That before the introduction of the formulation for Petrov-Galerkin, it was not possible because you had tons of oscillations for advection diffusion problems. Yeah. Okay. So yeah, we discussed Petrov-Galerkin. So now we just have to basically plug that back into the equation. So if you do that, here I'm doing it for one element, right? Obviously, you pick one element, that element has to be in equilibrium like every other element, right? So let's pick one element to make things simpler so that integration can happen on that element only. When you plug the trial solution, right? Now notice that I'm using lowercase symbols instead of uppercase symbols for the coefficients. And that is because now I'm at the element level. So to me, the uppercase U is actually comprising of all the degrees of freedom. But if I am at the element level, I use lowercase symbol for U and for W. So I just basically plug in those expressions that you saw in the previous slide. So I get this guy, and I plug that back into the variational form. And this is the expression that you get. Now, if you pick one element, right, you have only 2 degrees of freedom for that element, right? You have the left degree of freedom and the right degree of freedom, right? That's why we remove, of course, from the integrals these vectors because they are independent of x, so they can be taken out of the integrals. And so what you see here, right, this B is a matrix, is a so-called, no. This whole thing is a stiffness matrix. But B is so-called strain displacement matrix, okay? And it's called the strain displacement matrix very straightforwardly because it relates displacements to strains, right? So you can write basically the strain equals B times U at the local level. That's why it's called the strain displacement matrix. So again, if B is the derivative of the shape function vector with respect to x, remember that in our internal energy term, we require derivatives. You remember that in the variational form? Let's go back to that. I require the derivatives, right? So basically, if UH is going to be defined as phi times U, well, now I have to apply the derivative to that phi vector, and that is where this strain displacement matrix shows up. Yeah? Okay, so this first term, again, keep in mind that I'm still at the element level. I have not done any assembly yet to get the global system equations, but at the element level, I get this term. This here is going to end up being the stiffness matrix. This thing here is going to end up being the mass matrix. It's a consistent mass matrix because I'm actually integrating the shape functions inside the element. So I'm not lumping anything, although lumping is something that people often do in dynamics. And then everything that is on the left-hand side is a function of U, right? Everything is on the right-hand side is not a function of U. It's independent of U and ends up being the force vector in our expression, right? So I have here the body force term, and I have essentially the axial forces at the ends of the element, not the boundary conditions of our problem, where we were looking only at the ends of the bar, the reaction and the applied axial force at the other end. No, here I'm looking at the axial force at the elements only, right? And so this whole expression, if I say for all W's in certain functions space, that translates into all vectors W in R2 for that element. And I say R2 because how many degrees of freedom we have in that element? 2 degrees of freedom only. So the statement for all W in some function space translates to this statement here for all 2-dimensional vectors, simply because this is the unknown part of W. Remember, if I write W as phi times W, right? Phi is known, so I don't need to care about that anymore. The unknown part is only the coefficients. That's why that translates into all W's in R2, right? Okay, so when I do all that, then I get a final expression, as you see here, where this term here, as I said, leads to the so-called stiffness matrix, right? this term here is going to be called the mass matrix. These are all local matrices at element level, and then this whole expression here is going to lead to my right-hand side or force vector. And notice that there are no W's anymore, right? So what happened to the W's? They disappeared. Well, in fact that this expression here has to hold for all W's essentially means that this thing has to be equal to that, not to have, say, the trivial solution of W equal to 0 for making that happen. So this has to be equal to that in order for this to hold. And so we don't care about W's anymore. They disappear from the final formulation. And now we have our dynamical equilibrium equation at the element level. So notice we have KE times U plus ME times U double dot equals F. And that is my dynamic equilibrium equation at the element level. Okay, but you may argue, well, what happens? We don't care about one element. We care about the whole system. So what do we do? Assemble. So now, if we have our equilibrium at the element level, we simply do the so-called assembly operation, where we take the contributions of all these elements and we are adding them into the right places in a global system of equations to obtain the so-called global dynamical system equation, right? Which is mu, and again, since I'm at the global level, I'm using now uppercase symbols, and mu double dot plus ku is equal to F, where this A here is our standard finite element assembly operator. And we call it like that, right? So what is it? It's not that fancy. We just have to sum things at the right locations in the matrix. That's all it means. That means that if element 1 and 2 are connected, right? Well, I need to make sure that element 1 contributes to this degree of freedom that is shared, and element 2 also contributes to that degree of freedom that is shared, right? This is very straightforward. Everybody who has done any finite elements knows this. So the idea is that when you have your stiffness matrix at the element level, you complement that with the so-called element freedom table, right? Which is basically telling you how you're going to map those coefficients in the matrices into the global system, right? That's all it is. But that is a very standard, our finite element assembly operator is what we normally write in books, in papers. But again, it's just simply a matter of having proper additions so that our system is properly set. Okay, so now when we have our equation, well, now we have to solve it, right? Now, not so easy, right? Because we need more equations. We have here displacement and we have acceleration. And so we need to complement this equation with other equations so that we can solve it. And that is the basis of time integration methods that we are going to delve later in this lecture, for which we're going to really look at Newmark's family of methods. Okay? All right. So we stop here for 10 minutes. It's been a lot. Of course, you're welcome to ask questions now if you have any. If not, let's stop here for a few minutes and then we come back and we look at the same thing in 3D, and then we're going to do time integration.